the mission, why we want to get this thing right. Okay, we do this work in a number of different interrelated ways. We train engineers in disaster forensics, as we do in STAIR and in other places. We understand the balance between risk, exposure, and vulnerability, and we try to elucidate that and put it in language that the rest of the community, the society, the policymakers can understand. We design those structural methodologies based upon the building codes. We apply our knowledge into the building codes as well to influence what we do, and we have to convey these knowledge to the community. Part of that conveyance of knowledge is from these disaster reports that we do at STAIR, at FEMA, and other places you see there. Let's take one disaster. The 1970 Lubbock Tornado, okay? I don't want you to read all of this. It's not going to be a test here. Choose any two numbers, any three numbers that you wish to, and take those away with you from here, okay? The top three lines, 430 houses destroyed, 519 major damage, and 7,800 minor damage. If you add in all the houses that were destroyed, damaged, minor damage, apartments, mobile homes, that's nearly 10,000 structures which were damaged or destroyed by the Lubbock tornado. Okay? Comparing that to the number of businesses, about 250 businesses, comparing that down at the bottom, you see there are 531 fatalities that were occurred. This is what happens in any tornado, okay? But if I were to go to look at this here, what stands out to me as a structural engineer, if I was looking at who lives and who dies for that community, is this pattern has not changed in 50 years. Okay, 10,000 houses destroyed, 250 businesses destroyed. Where does the structural engineer work in this area? Have we done a good job in 1970, and are we doing a good job in 2020? That's a question that we have to ask ourselves. Okay, so in 1970, in May 1970, Kishore Mehta MacDonald conducted the area of the damage observations. It covered about 25 square miles. They did much of what we do today. They rated the intensity of the tornado from its immediate pathway and spreading out of that. And then they took case studies of 93 structures, and in which they enabled them to quantify the damage to these various 10,000 structures, etc., from their data set. Okay, and so this is what you will be doing. We are doing in STAIR is we go out there immediately, we look at structures, and we quantify and report. Okay, one of the early and important observations was the best estimates of wind speeds were no greater than 200 miles per hour. The second one, which is more important, and a finding which was known at that time, is that most of the damage sustained by structures were created by winds in the 75 mile per hour to 125 miles per hour area. Okay, so this is what we are about, to find out the evidence of what causes the failures and then do something about it. Okay. The other point I wanted to make here was that this is nothing new for structural engineers. Okay, nothing new for the practice of engineering in itself. The forensic engineering has been part and parcel of structural engineering from the inception. Okay, we have studied failures going from the 9/11 failures. We learned from that. The Kansas Hyatt walkway collapse, we've also learned from that. The forensic area for a natural hazard is a different animal. It's merely a bigger animal, and it is taking our focus away from what we have done in the past, which is looking at buildings one at a time, to looking now at communities, at the community resilience, and at the behavior of buildings. This paper was done, the journal Constructed Facilities, about 10 years ago, just to show us, as we all are academics, in the pedagogical area, we are keeping in tune with the ASCE body of knowledge. When we use forensic engineering principles, we can elucidate a whole lot about what our students need to be learning from and doing. And I would highly recommend that you use this so that you understand that not only if you're involved in STAIR can you help on the research end, but a lot of this information can be fed back into your classes and you know, improve that cycle of training of our next generation. So my research, as I said, primarily started as hurricanes and the performance of those. Hurricane Andrew, just before I started my PhD, Hurricane Hugo and Gilbert in the Caribbean. Of course, I am from the Caribbean, so this was profoundly important to me. What do you see? What am I showing you again and again is that the housing stock of these communities suffer the most. The non-engineered building suffered the most. And again, I ask the question, rhetorically in some sense, where are the structural engineers in this? What have we done right or wrong? That the fact that all these houses appear to have disproportionately so much damage. In 2011, about 9 years ago, we see the similar pattern of damage to houses, in particular from the tornadoes. Okay, so you have the damage in the thousands. Now the economic losses are in the billions, and in that year there were over 258 fatalities from tornadoes, one of the worst years after 1925 tornado. What can we do about this, and have we done enough? Okay. As in the case with the Lubbock tornado, you would find a team enters fairly quickly, identifies locations of the damage, and we try to quantify and rate what that damage looks like. I would say the major change that has made that possible, that we were able to do, is utilizing geolocated photographs, which now became data points in the 21st century. This did not exist in 1970 and in prior tornadoes as we went along. And in addition to making photographs data points, now we had the ability to pool information rather quickly using servers and uploading information in a much more efficient manner. And therefore, we were able to produce these maps within days of the team being back from a disaster, actually sometimes within, while we were there in Tuscaloosa, in order to get that done. And in so doing, forensic evaluations of natural hazards has moved from, excuse me, a 12-month period of turnaround to we did it in 3 months in this case, okay? Imagine we did this in April, early May. next month, May the 20th, we had another Joplin tornado, and we were able to turn that around and do an ASE report in that time. So therefore, the movement has been quicker. Another thing that we did here was on my group, the Wind Hazard Damage Assessment Group at University of Florida, we recognize, hey, wait a minute, we're just preaching to the choir. Everybody knows this, don't they? Why do we do what we do? Again, ask yourself, what is the role of the structural engineer in forensic evaluation and observation? And so we took it upon ourselves to do reports within 24 to 72 hours of the event. Why? Because social media has come leaps and bounds and enabled the sharing of information rather quickly. To the federal and trusted sources have been able to put their information in places where it's available for others to see. And three, much of this information was not contextualized so someone can actually make a decision about it. You know, you grab the information from National Weather Service, you grab something else from FEMA, you grab something else from the community itself. So we recognize that the skill that we possess, forensic engineering skill, is something that we can apply to share with the public who has been affected. And let's face facts, this is why we exist, to make the communities a little bit stronger. Okay, why do we want to do this? This photograph must have been taken in, I'm guessing, the end of May 31st or thereabouts in Joplin. I keep coming back to that building, that reinforced building in the back of the background. That's a Joplin Medical Center, St. John's Medical Center in Joplin. 10-story building that was right in the middle of this tornado. And the activity of going through this work, you know, it focuses your attention on the little teddy bear, on what family lived right here, where are they now, and how is this damage affecting communities. But more importantly, why? Why is this damage here? Why do we still have this type of destruction nearly 40 years at this time after the Lubbock tornado? Why was there not a building code, a tornado resilient building code before then? Okay. So that's the background. What we did was we used the PIs and we used that sort of philosophy, if you will, to develop the STAIR experience. Okay, and so led by Tracy Kajewski-Karaya, and we had these 5 areas in which we divided up, and what we did was we said, okay, well, everyone who is involved in STAIR is going to be involved with some sort of formal training as a structural engineer, or maybe an allied field. You know, a lot of the inputs we find is, it's not just structural engineering about. Okay? We also have levels of field experience from level 1 through level 4, in which all our members would find themselves suited. Okay? We do 2 types of investigations, one virtual and one in the field. And interestingly, they both work together to create that efficiencies that I talked about earlier. The vast virtual assessment structural team, they're sort of paralleling that wind hazard damage, preliminary damage reports that I did prior to for wind events. but now we spread to all 4 hazards. So that vast team can go in there, and be it, you know, the tsunami in Sumatra, or an earthquake, wherever it occurs, and we can collate that data in very rapid time. And that vast data is going to influence what we do as the field assessment structural team. Okay? The field assessment structural team, and there could be more than one for any particular disaster, they will be the ones going out there and actually doing the surveys. But they actually do rely upon the work that we do virtually first to get a better sense of where to go and what to do and how we will do it. After the field evaluation team, the FASTA, completes its mission, there is a data enrichment and integration set that we will be talking about shortly. Okay, so let's say we have an event. It is August. Let's pray we don't have an event right now, but this is the process. After we are monitoring the weather, the seismic events, etc., or someone from the community might reach out to us and say, you know, Puerto Rico, we will get something from here. Can we do this and that? Okay, we're in communication with all the other NHERI nodes, and in particular Converge, and then we establish what we're going to do. For major hazards event with little potential to generate new knowledge, we might produce an event briefing, which is a shorter document just articulating what we see from virtually with no follow-up action. With major events where potential for generating new knowledge, we will then activate the VAST, and then ultimately at the end produce a preliminary virtual reconnaissance report, a PVRR. Okay, and it is that document that is useful for the FAST in its planning and its implementation. When we have a major event with ability to generate new knowledge, we may continue that VAST, activate a FAST, and then the output of that is going to be an early access reconnaissance report, an EARR. Okay. After that, there are a couple more weeks and days, we will have that report being curated and the data sets uploaded into the NHERI Design Safe. Okay, and this happens rather quickly, and this is why we need a lot of members who are trained and ready to go at any given time. Okay, so we want to have the PVRR preliminary virtual report released in 2 to 3 days after an event. Okay, we want the EARR report about 48 hours following the return of the FAST team. The FAST team might probably be out there a week after the event, stay a week. So therefore, within 20 days, we want that report on the floor. Okay, and our intent is that you have a curated data set available for the community to then use within 30 days of this. What does this report get used for? Primarily at this time, it is used by the National Science Foundation in its deliberations when you apply to the NSF for rapid support and awards. We have several door-to assessment technologies that are used. The door-to-door damage assessment, which is a major part of this work, looking at a survey implement that we just look at one building after a time, hence the name door-to-door, and we use an app on our smartphones called FULCRUM. We use unmanned aerial surveys, Street View, Google Street View type camera technologies, as well as terrestrial scanning technologies. All of these come in here and are being used. Okay. Part of the infrastructure and the reason why we have this surgical type strike methodology is, and I'm going to give real props out here to Tracy for coming up with this, because this is way beyond my T-Rex abilities. But we are truly engaged in a collaborative environment, from using Google Docs, all Google software, Google Docs Present, which I'm using right now, and we use the design safe Slack channels, a channel for every event. What you see here is the channel for Hurricane Dorian following last year's 2019, and then we use a FULCRUM, which is seamless between phones and applications and going on to other things. Okay, so we're really familiar with this, and it has made tremendous steps forward. So what I'm going to show now is the workflow plan for this, and I'm going to go through a little quicker here. Basically, we have things that we do at pre-deployment, during deployment, immediate post-deployment, and long-term post-deployment. Okay, so for all of these items, we have places where we can go and things that we can go through. Okay, in the pre-deployment tasks, again, it is utilizing the information we have got in our PVRRs, the satellite imagery, etc., and we actually maybe try to get some target location so we have an idea of where we will be going to. In the data collection system, we have the door-to-door assessments that we talked about. We use the drones in combination with that, both for orthomosaics as well as to get a far better idea of what the roof area damage is. And then we use Street View to fill in the gaps between areas that we have not actually seen directly. Okay, and we leverage all of these technologies here, utilizing the FULCRUM app. We're able to record photographs, video, as well as audio, which has been a very useful tool that we're going in there, as well as free-form text. The nice thing about using the FULCRUM app is it is in real time. We are sharing data once the cellular systems are up and running in the disaster area that we're going. And even if that breaks down, we can then get back at after the day's work and sync over Wi-Fi, etc. Let's see what the data responsibilities might be between the VAS and the FAS as we go along. Okay, so if we look in the wind, building, say Hurricane Irma 2017, somewhere down in the Keys, Monroe County, it's lost its roof, the wall cladding is gone, a window fenestration might be broken. We want to know how much wall sheathing is damaged, and so on and so forth. So these are the types of things that we would want to collect: the percentage of roof damage, the percentage of wall cladding failure, etc. Other attributes. This was something that we had not done beforehand because we just didn't have the photograph as a data point. Now when we have a photograph of a data point, we put it in a database, and now we collect the year built, types of occupancy, footprints, roof slopes, a whole host of other metadata related to this device. Here we can show the distribution of the work between what someone might do in the field versus what we expect the vast team members will be able to do back on the ranch. Okay. We use other information from other data sources, etc., and then at the end of this process, we go through and we do the data enrichment and quality control, which is absolutely important for us going forward. I think, I need to go on a little bit fast through that, but essentially, everything, the investigation notes, the building attributes, structural details, walls and foundations, all of these things are important, and some of them will be depending on the particular objective of your forensic evaluation. Some may be more or less important as you go along. Okay. So to reiterate, the benefits of STAIR is we want to be early in there. We want to have a network or utilize our network of regional nodes so that we have access points. We work closely with the rapid arm of NHERI, who have ready to go the equipment, the technical equipment that we would need, the street view cameras, the drones, etc., and even some of the handheld tools that we need. We want to be efficient, so we are trained, all our members are trained, and we continue to beef up our training as we go along to streamline that data collection, okay? And most importantly, we want to be impactful. And I would say that impactfulness starts here, where we as structural engineers, we as natural hazards professors understand how important it is to train that structural engineer, that no longer can you say your work begins and ends when you're working for that one client. Okay, that's no longer what we do. That is a 20th century approach. We have to consider the resilience of the community. We have to consider the resilience of all of us. And so finding our ways, finding our voice to speak out about why do we still have 10,000 structures being destroyed in tornadoes 50 years after the 1970 Lubbock tornado. That is part of our work. Okay? So looking back at the value to STAIR members is you are able to go out there or see virtually information that you can use directly into literally every single course that we teach as structural engineering professors. Okay, we can use and share the information that we gain immediately with the community that has been damaged. Okay, we don't need to wait for a peer-reviewed manuscript that comes out 3 years later after all those houses have been reconstructed the same way that they were prior to the hazard. Okay, as researchers, then, this was a question we asked before earlier this year, or not last year. Okay, we want you to use this information to generate new ideas, okay? To deepen your expertise in hazard-resistant design, to learn about as-built performance of structures. And all of these things are available and well within our capabilities to do. So with that, that is my presentation. I would like to acknowledge US National Science Foundation, and we are part of the Converge Node and wider Extreme Events Consortium. So if you're not a structural engineer, there are other places in which they're doing pretty much the same types of things on the work here. So if there are any questions, I think I see a few questions here. I have maybe 2 more minutes and I can take some.
Yeah, David, I'll help you navigate those because I've been dropping some links in to help people find the resources that you were alluding to. Greg had a point about talking a little bit about our data standards and the way that we ensure that we have this objective assessment of damage using the component rating systems that we have standardized in our handbooks. So I don't know, I can drop the link into the chat to show everyone where to find the handbooks that basically show our members how to rate damage in a consistent way. But maybe you want to mention how we do that at the front end and the back end through the data enrichment and quality control process while I drop that link in.
Okay, sure. Thanks a lot, Tracy. No, this is important because, again, we're not the first to be doing this, okay? And we're not the first to actually try to, use some whoop-de-doo tool to combine things. This has been, the bane of structural engineers' lives for a long time. What we recognize through trial and error is that there is need, in order for our data to be relevant and useful, we have to have some standards of quality, and that begins with our training in terms of how we interpret different things. If you go, once you become a member of STAIR and you have your FULCRUM app on your phone or your desktop, as you enter the data there, you will see at the lower end of those screens, there will be a place for us to just do the DEQC parts of it, okay? And this is all done by the VAST team after the event, whereby we go back and we're checking the entries of the field team, as well as, almost randomly checking those informations as well. Okay, the training is and the standards are quite elaborate. If you can go to the links that Tracy is putting up there now, so you have a good description in words as well as in photographs to do what we do.
Thank you, David. And I would, you can see what I'm bringing into the chat has a link to our resources tab, which has the handbooks, as David alluded to. And we also QC code every entry. So in addition to kind of enforcing those standards, both hoping and helping our field investigators do the assessment accurately in the front end, as he noted, afterward it goes through a quality control process, and those standards are enforced on the back end, and every record receives a QC code. So if you wanted to use the data to calibrate models, for example, you could make a choice to only include data that reaches the highest QC code to prune down the data set so only the most reliable data is used. And again, all that data is available on our Fulcrum community page, which is hyperlinked, and it's available in real time. So even while it's being quality controlled, you can see the data in its various stages of progression. You don't have to wait the weeks and even months it can take to get all the data quality controlled and into design safe. You can start working with the data as it's going through QC and seeing the data almost in real time. So hopefully that was helpful in the chats that, that we were capturing these, and those links are all there. The question, one question came from Elena, is it possible to extend this to Canada? David, maybe quickly you can comment on our approach to how to take this beyond the US and how we have already.
Right, yeah, so, don't think of this as just a learning that we can only do in the United States, okay? We have been through Sumatra, we have been through, Algeria, crap, I just messed up that country.
Albania.
Right, but so
Bahamas, Victorian.
Bahamas as well, right? I have worked with Greg Kopp at Western University. I've worked on various standards for tornado resilience in the Ontario province as well, and so there is good synergy between the forensic work that we do here and what exists in Canada, and a lot of similarity between the buildings. Greg has also worked with Forest Masters on a hurricane damage or during hurricane assessment. So we know a lot about each other's work.
And so with that, you know, I think we'll have to pause this session and continue questions. Perhaps we'll catch some and address them later. I just saw that, I just noted that our app doesn't care where you are. It will do the geolocation wherever you are on the map. My only caveat is our manuals for quality control and some of the classifications of damage are largely rooted in US practice because they're derived from HAZUS. But I will note that we have expanded the supported typologies, much of that motivated by the work in Puerto Rico in responding to Hurricane Maria, and then of course it parlayed over into the earthquake, to be able to classify typologies that are not primarily wood-based, but load-bearing masonry and other forms of confined masonry and reinforced concrete frames. So we have expanded the typology support, though much of it was derived early on from the performance of wood frame construction. So we are continuing to grow over time. So with that, I think we will transition. I know we drifted a little bit off schedule, but there were some great questions and clarifications that we offered there. And my job is to actually close us out for today. So I will do my best to get us on time.